Welcome everyone to tonight's Alkyne reactions practice session. Again, to get the notes in the worksheet, livestream.com/or/go-live, that's the pinned comment. The focus of today's session is not just to solve a couple of Alkyne practice problems. I want to use each problem as a starting point for a discussion about strategy, about tricks and tips and shortcuts and things that you want to look out for, so that you're looking at problems like this in the future from a perspective of logic and understanding, rather than just something you memorize and may not always know how to apply. With that, we'll start with a quick warm-up problem just to get you going. We're given an alkyne and asked to react it with HCl in excess. What happens when you have these conditions? What is your product? More than just what is your product, the question I want you to think about is, how do you even approach this? So the way we start something like this is evaluate what you have. I see that I have an alkyne. It's a 4-carbon chain. Remember, that's 1, 2, 3, and 4. And I'm reacting it with excess HCl. I know that HCl is going to add across the pi bond. We're not doing the mechanism. We want to still understand it so that we can quickly come up with the answers. If HCl is going to add across the pi bond, we know that each time a pi bond breaks, we add a molecule of HCl. Excess tells me that I have more than one and I can add as many as I need. And that means for my final product, I still have the 4 carbons, but this time, because I no longer have a triple bond, that is an an sp and another sp hybridized atom. sp 180 degrees linear, that's why the starting molecule is drawn this way. But the product no longer has the pi bonds, and so I'll break the first pi bond and I'll put the first set of H and Cl. I'll break the second pi bond and put another set of H and Cl, where the hydrogens add to the same carbon and the chlorines also add to the same carbon. Hopefully that was a nice and easy question. If you have any questions on it, go ahead and type it in. Not just questions on what I did, but anything related to the logic, the reaction, just anything about this that you'd like to understand more, go ahead and type that in the comments. The next question, we'll still keep it simple. We're still warming up. I'll give you a molecule that looks like this, and I want you to react it with... Where's my problem? Right here. Br2, also in excess. Now you can have excess written on the bottom, you can have excess written on the top. Sometimes you'll even see it written as the letters X and S, and that simply tells you you're adding more than one if possible. Question, is this going to be recorded in your YouTube channel? Yes, this video will be on my YouTube channel, and if you sign up at layerforsci.com/or/go-live and see the link in the pinned comment, you'll get a link to the recording, to the worksheet, and the session notes. Once again, we have an alkyne. We know that the alkyne has 2 pi bonds. That means it can react twice. Every time I break a pi bond, I want to add bromine to either carbon, and so we'll start with redrawing the skeleton. Because the skeleton changes, I always like to number these problems just to make sure I have the right number of carbons in my final product. I have a total of 6. 1, 2, 3, 4, 5, 6. You don't have to number the product, it's just to make sure you have it right. We'll start with the first pi bond. I'll break it. It's a pi bond between 2 and 3. That's carbon 2, that's carbon 3, and so I add 1 bromine to each of these carbons. I'll break the second pi bond and do the same thing again, 1 bromine to each of these carbons. And that gives me a final product with 4 bromine atoms spread across the 2 carbons. Alexandra, very likely. Alright, if you're finding this easy so far, give me a thumbs up in the comments. I think you can hover over that heart. Oh, I guess there's no thumbs up. So give me a party emoji in the comments, and we'll go to the next question. Any questions on this, of course, go ahead and type it in. What I find is that if you have a ring, It doesn't matter how difficult or easy the problem is. Just seeing a ring automatically makes the problem look scarier. Let me know in the comments if that's the case. You see a molecule, you should know how to react it, but something about that ring just makes it look very scary. And we are going to react this one with H2 in a Lindlar's catalyst. So let me know in the comments what'll happen if I react this starting alkyne, did I say alkene? I meant alkyne, with H2 in a Lindlar's catalyst. Question, why are 4 pi bonds broken rather than 2? No, it's not that I have 4 pi bonds broken, it's that every time I break a pi bond, I add an entire molecule of Br2. And so for the first pi bond, going back to the last question, I had a Br2 that added across the pi bond, one here and one here. That's a very good question, by the way. And for the second one, once again, the pi bond breaks and I have a Br2 being added. That's this one and this one. So even though I'm adding 4 bromines, it's only 2 pi bonds that I'm breaking to get the 4 bromines onto the molecule. Question, if the Br wasn't in excess, how would you know which carbon would get the Br? Oscar, that is a very good question, and I want to come back to that, so I'm just going to put a note here for limited, and I'll show you something about this problem. Okay, so going back to the one I have on the screen, the first trick is that when you see a molecule that looks scary, I challenge you to ask yourself, what is actually happening here? I have an alkyne, and it's undergoing a reaction. Does the ring play any part in this reaction? For the sake of the alkyne reaction, no. And so to make this problem look less scary, just put your hand over the rest of the molecule. It disappears. Everything else is exactly as you've studied, and you're good to go. If the molecule is too scary, just do that. Cover it and work on the part that you know. An H2 Lindlar's catalyst is going to give me a partial reduction. And the partial reduction is going to be very specific in how it happens. Let's see, did anyone give me cis? They did not. We're going to get a cis alkene. This has to do with the fact that we have a metal catalyst that grabs it from one face and the hydrogens will slide on together, very similar to what we did in yesterday's live stream on alkene reactions. And so to come up with a final product, we'll redraw the skeleton, but this time we'll do all the bonds in zigzag. We won't do anything linear because we're breaking the sp triple bond. And that means I have 1, 2, 3, 4 coming out of the benzene ring. That's 1, 2, 3, 4. The pi bond is broken between 2 and 3. That means if that's 1, this is 2 and 3, but no, I said cis, so this is wrong. All we're going to do is flip it. This gives me a cis alkene. How do I know it's cis? If I highlight the pi bond, then I can draw an arrow coming out of it to each carbon. And when the arrows go in the same direction, cis, like sisters on the same side, that's how we know it's a cis alkene. If I had an arrow this way, one up, one down, that's trans. They transfer away from each other. But in this case, we want the cis alkene, giving me that as my final product. Niranjan, I'm going to come back to that one as well. That's a very good question. So when we use a Lindlar's catalyst, we always get cis. Yes, if it's an internal alkyne. If it's a terminal alkyne, you won't, because a terminal alkyne does not have cis or trans, or rather a terminal alkene cannot be cis or trans. So let's take a look at propyne. If I react propyne with H2 and a Lindlar's catalyst, I break the pi bond. And my only option is to draw the molecule, the skeleton like this, with a pi bond. There's no cis and no trans because I have a hydrogen here, and I'll show the second one in green because it came in from here, and I'll also show this one. Well, technically, That is incorrect. It's the two green hydrogens adding to the same side, and the gray hydrogen is what I already had before. So let me know, for anyone else who was wondering, if this answers your question and this clarifies. A Lindlar's catalyst will only give me a cis-alkene if it's internal. Let me add that to the notes. For an internal. But it will not give me cis or trans for terminal, because there is no cis or trans when we're talking about terminal with two hydrogen atoms at the end. Big Al says, Leah, you are amazing. This is extremely helpful. Thank you so much. That's really sweet. Can you do lots of questions that involve multiple steps? I'm actually planning to do that next week, so make sure you sign up. See the pinned comment for the URL to get notified about next week's sessions. Okay, so let's go to, I forgot who asked, but what happens if we try to limit what we react when the reaction should be in excess? If I have an alkyne, let's go with a simple alkyne. If I go with propyne, some professors will give you a reaction that looks like this, and they'll tell you HCl 1 molar, meaning you don't have excess, you only have 1. And the answer they want you to give is as follows. One reaction means you only break 1 pi bond, and you add the HCl, Markovnikov's rule, chlorine goes more substituted, hydrogen less substituted. This is the correct answer if your professor teaches it that way, but it's technically the wrong answer, because you're not reacting 1 alkyne in a test tube with 1 HCl. You're reacting 3 million alkynes in a test tube with 3 million HCl. And that means, in reality, if I were to just zoom in on 3 alkynes and 3 HCls, here are the 3 different products I'm going to get. Product number 1 added in excess, chlorine, chlorine. Product number 2 only added 1. Product number 3 is actually no reaction because we used up all the chlorine. So in reality, you're going to get a mix. There's no way to control where the chlorine goes. So here's what I want you to do. See if your professor taught it this way. If you're not sure, ask your professor, because on some exams this is the required answer, but in reality, this is what happens. Again, think of it logically. How are you going to control this? And I'll give you a real-world example. On Thanksgiving, we were at my in-laws, and one of the highlights is watching my baby interact with their dog. She is the cutest, and they are so adorable together. My in-laws' friends went away for Thanksgiving, and so my in-laws were watching their dog as well. Now, when they feed the dogs, they have 2 options. Option 1, put food in 2 different rooms. Each dog goes to their significant bowl and eats it. Option 2, put 2 bowls, where, just like this reaction, you have bowl number 1 for Gracie, bowl number 2 for Greta, and you'd think that they would each eat the same amount, except Greta eats very, very quickly, eats her own food, or was that Gracie's bowl? Greta eats her own food, then comes over this way, pushes Gracie out of the way, and eats Gracie's food. That is what is happening here. You can't control it when you have so many reactants just in the same container. Let me know in the comments if that makes sense, and also let me know if your professor teaches it this way. Beyonce, which specific internal problem? So then another question came in regarding the halogenation. Even though the intermediate is not isolated, if I want to show what happens step by step, this time I'm going to show you the Br2 again. The first intermediate that is not isolated is going to look like this. A pi bond and 2 bromine atoms added. The second reaction is going to look like the product we expect. And so why am I doing it that way? So we break the second pi bond, and now we add across again. So what I want you to recognize here is that it's not the bromines adding at the same time from the Br2. Every molecule of Br2 that gets added adds across the pi bond to one carbon and the second carbon. And when the second Br2 molecule comes in, that is how you get 2 on each one, but they never add together. Again, I forgot who asked that question, but hopefully that is clear. Beyonce, I'm not sure I understand your question, so try to explain exactly what you didn't understand, and I will go through it for you. Alright, so let's crank it up a little bit and go to, let's do a backwards question. Because a lot of times your professors know that you memorized your reactants and products and they want to change it up. So they'll give you, I marked that question as medium. That's not a medium question. Alright, let's go for it. I have this one next, but it is not medium whatsoever. We have a starting molecule, and under whatever reaction conditions, as many steps as you need. The only thing you're told is that this is an alkyne of 4 carbons. You have to come up with a product that looks like this. 4 carbons, and a chlorine here, and a chlorine here. So what I'm looking for is not just the answer, but I also want your thought process. How are you going to approach something like this on your exam? Niranjan, this first problem, if you do hydrohalogenation, same thing. It's an H and a Cl that add individually. Why did I do that? So the H will add, the Cl will add, then the H will add, and the Cl will add. That is how you get 2 on the same carbon, and that is the sequence of steps. So this is a little bit tricky, because if you think about it, what do you already know? So you don't want to jump right into, let me come up with a molecule. I want you to look for clues in the problem. If I know I have a starting alkyne with 4 carbons, well, that's very easy. It's 4 carbons. The pi bond has to be in the middle, between carbons 2 and 3. How do I know that the pi bonds are both between carbons 2 and 3? If I look at my product, 1, 2, 3, and 4, if chlorine adds to carbon 2 and carbon 3, that means that's where the pi bond would have had to be so that I can break it. But now the question is, what reaction do you know that is going to give you a vicinal dihalide from an alkyne? Vicinal, they are in the vicinity, they are next to each other. Dihalide, 2 halogens, as opposed to a geminal dihalide, which is where I have 2 on the same carbon. A gem, you want to hold them both at the same time in the same hand. Vicinal is in the vicinity, in the neighborhood. If we think about the reactions, to add 2 chlorines, I would think of, well, don't forget, we also have an H here and an H here. Well, do I want to add 2 molecules of HCl? Do I want to react this with HCl in excess or in 2 molar? No, because this is going to give me an intermediate that looks like this. Hydrogen and chlorine. And then to get the second one, this is a not isolated intermediate, it will continue to react with HCl to give me, well, I have hydrogen and chlorine. And what did we say about this reaction? The second hydrogen adds to the same carbon as the first, and the second chlorine adds to the same carbon as the first. This is most definitely not the same thing. And if this is not the same thing, then what other reaction can I use? Well, what if I use Cl2? Because that will add the chlorines to 2 different carbons. So let's try that one. Cl2 in excess or limited, because I already showed you that it's going to jump all over the place, I would get a molecule that looks like this. Too many chlorines. And if somehow, some way, I manage to isolate the intermediate, because some of your professors will ask for it that way, my intermediate is going to look like this. I have the 2 chlorines and I have a pi bond. So that is still no good. Not what I'm looking for. Nope and nope. So here's where you want to ask yourself, if I can't just put in some reactants that I memorized, what if for just one moment I ignore the product and treat this as a brand new problem? So let's take this as a brand new problem and ask the question differently. And this is what I'm going to focus on extensively in next week's live stream, where I do synthesis and reactions, multi-step reactions. The question we want to ask is, if the starting molecule was irrelevant at the moment, what reaction do I know that will give me 2 chlorines on any molecule? Forget an alkyne, any molecule. Well, I know that if I react an alkene with Cl2, then I only have 1 pi bond to break. Then I break that 1 pi bond, I just get 1 chlorine each. And I see the correct answer from Graceland, from Niranjan. Let me know if I'm butchering your name. I want to try to pronounce it correctly. From Big Al. Excellent. Yeah, first I turn it into an alkene. And so now the question is, if I know I had an alkyne as my starting molecule, and I know I have to turn it into an alkene, all I have to do is fill in 1 more reagent. By ignoring the starting molecule and focusing on the product, I was able to take it 1 step back and treat this as an easier, simpler problem. And this one's pretty straightforward. Because I chose to do a transalkene, I will use NaNH2 in liquid ammonia. This is a radical partial reduction, a radical intermediate. What am I doing? Not NaNH2. That was that's the reaction I keep telling students not to confuse, and I just confused it. I think I caught NaNH2 in the comments and I followed up with it. No, it's sodium metal or lithium metal. So this is dissolving metal reduction. And dissolving metal reduction is where you use a neutral metal, like sodium or lithium. The reason I put that radical there is a neutral sodium, because it's on the periodic table, the very first row, it's group 1, that only has 1 valence electron. So in its neutral state, it's a radical. Very unhappy, very reactive. That's how we get the product. And from here, it's a very easy 1-step reaction to give me the vicinal dihalide. I'm seeing quite a few questions coming in about previous reactions. Make sure that you go back to the recording and watch that part again. And if it's still not clear, comment on the recording. I will be monitoring comments almost every day through finals, because I want to make sure I can answer all of your questions. Chemicopia, you are very, very welcome. Question: my teacher told us that Cl2 and CCl4 also gives vicinal dichlorides. Does that work too? Well, this right here is what you're talking about, Cl2 in CCl4. Yes, I just didn't give you a reagent, but that is correct. A vicinal dichloride is the right answer here. Now, the NaNH2 that I told you not to confuse, let's take a look at that real quick. If I have a terminal alkyne and I want to do a chain elongation reaction, that was my most recent YouTube video if you want to see the mechanism. NaNH2 is how I'm going to accomplish it. Dissolved, that's supposed to be a 2, dissolved in NH3 liquid. This will give me the deprotonated alkyne, a good nucleophile, and that's a completely different reaction. So this right here is not the same. Alright, so this one right here, let me know if you have any questions on this reaction. And as you can see, not a medium question. I don't know why I had it as the first question on my medium list. But hopefully you learned a lot out of it, so hopefully it was worth putting it as the next question. Alright, on we go. Next, we have a molecule that looks like this. As a reminder, this session is being recorded. To get access to the notes from tonight, the worksheet, the problem set that I'm working on, and information about the recording and more, go to the pinned comment, leahforsci.com/orgolive, and that's where I will email you everything afterwards. If you're watching the recording, you can still sign up on the same link and you'll still get everything after the fact. For this reaction, we are going to react this molecule with ozone, O3. What happens if I react an alkyne with ozone? And this will be an aqueous workup, so we'll put some H2O. Your professor may not show that, but just in case, I want you to recognize the solvent. This is a cleavage reaction, oxidative cleavage. And the trick is to find the pi bond that you're breaking and just slash right through it, put an oxygen into each position, and then carefully pay attention to your chain. I have a ring with 1 and 2 carbons on it. So for my product, I have a 5-membered ring with 1 and 2 carbons on it. For the second piece, I have carbons 3 and 4. Just 2 carbons that I numbered 3 and 4, so we could add 1, 2, 3, and 4. And then, notice how I added 2 oxygens for each break. Those 2 oxygens go on the end as a carboxylic acid. 1 oxygen, and 2 for a shortcut to get you the oxidative cleavage products. I see a question over here about why I didn't go cis. You could just as well have done a cis product. Because I did not give you any chirality, it doesn't matter. But if I gave you chirality on the final product, then you would have to consider if it came from a cis or trans alkene and answer accordingly. But because I didn't, either option, dissolving metal reduction or a Lindlar's catalyst, would have both given you the correct answer. Alright, I'm seeing a lot of questions on naming. I'm going to challenge you to come up with a name and put it in the comments. Alright guys, what do you think? Are you with me so far? If yes, let me know how you like, for those of you who are on the live stream for the first time, because I know some students came yesterday. So let me know what you think of these kinds of sessions. If you want more sessions, let me know what type you like. Yesterday we did a mechanism breakdown. Today we're doing practice problems. And for next week, so far the topics I have on the list are substitution elimination reactions and multi-step reactions. I may do 3, so let me know which ones you're interested. And if you are, go ahead and just hit that heart button again. Let's get some hearts going in the comments. Actually, how do you give this video a thumbs up? If you guys know how to do that, go ahead and give this video a thumbs up. And let's continue with this one. Okay. I'm debating between, do I go easy or do I go hard? I spent half an hour writing this quiz with a mix of easy, medium, and hard questions, and now I'm just trying to decide which ones to use here, because we're not going to do them all. But you can get the entire worksheet, even the questions that I'm not solving with you live, if you sign up for the notes and the worksheet at the pinned comments. Alright, we have this molecule. We're reacting with H2 and a metal catalyst. What happens? Anytime you have a pi bond, be it alkene or alkyne, if you have nothing there to slow down reactions, it will do a complete reduction. Every single pi bond is going to break. So while I work out the product, go ahead and let me know in the comments the date of your Orgo final exam. I'm going to start by numbering the chain, just to make sure I don't miss anything. I have a total of 6 carbons, 1, 2, 3, 4, 5, 6, with a branch coming off of carbon 3. 1, 2, 3, 4, 5, 6. What do I have to add to this molecule? Absolutely nothing. This is my final product. Every single pi bond was broken. Now, I want to show you, I'm going to add the hydrogens in, not because you're supposed to, but simply because I want you to see what happened. This pi bond broke, and I got 2 hydrogens. This pi bond broke between 4 and 5, and I got 2 hydrogens. And then this pi bond also broke for 2 more hydrogens. Again, in line structure, you don't have to show the hydrogens, but because this is a teaching session, I'm showing you so you can see exactly how the starting molecule relates to the product based on what we just did here. All right, finals I'm seeing Tuesday, December 19th. Wow, that's late. December 13, 11, 6. Oh, 12, 6. That makes way more sense. Saturday, December 11th. Wow, so there's a nice range of dates here. All right, let's move on to, I saw in the comments, do the hard ones. So what say we jump to, anyone against just doing advanced problems from here? See another December 13, December 7, December 11. Not seeing any objections, so let's go for it. My starting molecule is a very simple 2-butene. My product is a very simple 2-butyne. Easy peasy. All I have to do is convert my alkene to an alkyne. How do I convert an alkene to an alkyne? If you're thinking I have no idea, it's because there is no single reaction that goes from alkene to alkyne. Again, a tricky problem because it's pretending to be easy, but it's really not. And so, like we did in the last tricky problem, I challenge you to ignore the starting molecule and instead ask yourself, what reaction do I know that can give me an alkyne? Forget the alkene starting molecule, just anything at all whatsoever that you know can give you an alkyne, and that would be a double elimination. If I want to do a double elimination, then I need a molecule, that arrow is backwards, I need a molecule that can be eliminated twice. What molecule can be eliminated twice? A dihalide. So I have the option of putting both chlorines on the same carbon or both chlorines on neighboring carbons. Then the question is, okay, so which one can I make from an alkene? Do you know an alkene reaction that puts 2 chlorines on the same carbon? I don't. I know an alkene reaction that'll put 2 chlorines on opposite carbons, or let's do bromine because we've done chlorine before. So we'll put a Br2 here, or a Br on each one, and I kind of jumped ahead with the reagent. And now I can go ahead and fill in my reagents. To go from an alkene to a dihalide, this is simply halogenation, Br2, in an inert solvent like CCl4. Then I will do a double elimination using NaNH2 in NH3. Similar to what we saw before for the chain elongation, this is another type of a reaction, another incident. This is another situation that you're going to use NaNH2 in NH3. This will give you a double elimination, and that is how you get your alkyne. Question. So Niranjan, yes, exactly. A lot of students will look at this and think, oh, reduce it. But that's if you're trying to go from an alkyne to an alkene. The trick here is your professor knows you're thinking this way. Your professor wants to see if you can think that way. And all you have to do, very simple, ignore the starting molecule, come up with an intermediate that makes sense, and then solve the easier problem that is just starting molecule to intermediate. All right, let's try another one. And if you have questions, go ahead and type it in. For this next problem, you have to come up with a starting molecule that is an alkyne, however many carbons that you want to come up with, using whatever reagents and steps necessary to give me a final product that looks like this. We have a cyclohexane, a methyl group coming out of it, 2 carbons coming out of it, and an aldehyde. Christina, next week, make sure you sign up at layforsi.com/orgolive because that's what I'm going to cover next week. Question, is the foundation to these memorizing reactions? Absolutely not. No, no, no. I mean, technically yes, but you don't want to memorize for the sake of just memorization. You want to use an active memorization technique. So I'll put the link for you here. This is my YouTube video on how to memorize with an active method that will actually let it stick. This is how I finally learned mechanisms, because I started doing an active approach as opposed to just blind memorization. The first time I took organic chemistry, did blind memorization, I was failing the class. The second time I took organic chemistry, that was my secret. Nirmal, I don't understand your question. Alright, so let's take a look at this molecule and ask, what is the functional group? What is the part of the molecule that looks like it could have come from an alkyne? The only functional group that I see is an aldehyde at the terminal carbon, and that means this had to come from the alkyne. The alkyne had to be right here, like that, and that gives me my starting molecule. I have a, oh, that box is way too small. Let's make it bigger. I have a starting molecule that has the same skeleton with a methyl group here and 1, 2, 3 carbons, but because it's an alkyne, it's linear. sp hybridized means linear, and I have to draw it slightly different. Now, let's fill in the reagents. What reaction do I know that will give me a carbonyl from an alkyne? There are actually 2 reactions. I can use oxymercuration or hydroboration. The difference is, if I use oxymercuration, I will get a carbonyl at the more substituted carbon. If I use hydroboration, I will get the carbonyl at the less substituted carbon, because this is a reaction that follows Markovnikov's rule. This one is anti-Markovnikov, and now I know my steps. Step 1, I will use something related to boron, so your professors will show you a couple of different ones, BH3, B2H6, 9BBN. For the alkynes, you tend to see the bigger boron, so for example, B2H6, that's step 1. Step 2 is going to be NaOH, H2O2, and some professors want you to put water, but this is typically the accepted reagent. Question, how come sometimes CCl4 is put and sometimes my professor doesn't put anything? Abdul Malik, your professor is probably just taking the easy, let me just give something and not bother with the rest. So for example, some professors will just put this and ask you for the product, but they don't always give you everything. I see a question here. Oxidative cleavage to a carboxylic acid and mildly reduce it to an aldehyde. That could also work, but then you're going to have a side product for the other cleavage carbon or however many carbons you had on your chain. The way to do that and make sure you have no side products, I wouldn't even have thought to go that way, is this. We'll take 1 and then 1, 2. I'm going to have to draw this a little bit differently. So we have 1, 2, we need 4 carbons, 1, 2, 3, 4. And then attached to each one, we'll have the ring, like that. Because now, if we do step 1, oxidative cleavage, step 2, partial reduction, you're going to have no side products, you're just going to have double the amount of products. Very clever, would not even have thought to go in this direction, but I like it. Description, no, but that is a good point. So ketoenol tautomerization will happen automatically. You don't have to show anything for it because the conditions are already set, and it will immediately go from the keto form to the enol, from the enol form to the keto form, where technically here it goes from the enol form to the aldehyde because it's not a ketone, but it's still called ketoenol tautomerization. Question, how do you determine what reagents to use for each mechanism? This right here. In fact, with finals coming up, I'm just covering one topic right now, but if you feel that you need a good in-depth review on everything organic chemistry, we're doing a couple more live sessions with I have a private membership group where I have a complete in-depth library, kind of like this, but in a lot more detail and a lot more structured. Orgo 1, Orgo 2, beginner topics, intermediate, advanced, so I have reactions and problems and all of that. The link, if you're interested, and I'll also include it in the email if you sign up to get the notes, is layerforsci.com/join, and this page will give you all the information for the study hall. So if you're struggling with some of the reactions, if you want to see a lot more in-depth walkthroughs of problems just like this session, go to layerforsci.com/join. All right, let's continue. For the next problem, which one do I want to do? Let's do this one. If I give you a starting molecule that looks like this, and I ask you to react it in a series of steps. Step 1, NaNH2 in NH3, and then step 2 with this right here. This is a multi-step problem that if you don't have a lot of time on your exam, you don't have a lot of time to work the whole thing out. So I'm going to show you the step by step, and then I'll show you a quicker way to do it. So for this reaction, the first step is the NaNH2 is going to grab the hydrogen from the end. So this will be an acid-base reaction. NH2 minus grabs the hydrogen, gives the alkyne back its electrons. This will give you a deprotonated terminal reactive alkyne, a very good nucleophile for an SN2 reaction. We'll show a lone pair negative charge. And if I then react this molecule with this alkyl halide, a 3-carbon chain and a bromine, this will undergo an SN2 reaction, kick out the leaving group, and the final product looks like this. I'm going to flip the propyl group around so that you can see it. The new bond between where the carbon got attacked, the bromine left, and the alkyne added on. The alkyne is 1, 2, 3, like this, with a tail, or a branch at the end. This is the mechanism, the step by step. But if you want to do this quickly on your exam, first you want to understand what is going on. We see an alkyne. We know that a terminal alkyne reacting with a strong base in ammonia is going to have a deprotonation happen. And that should immediately clue you in. If I'm deprotonating my alkyne, I'm turning it into a nucleophile for an SN2 reaction. That means this is going to get attacked. As soon as that's what you identify, here's what you do. Redraw your starting molecule exactly as you see it. Add a new bond between the terminal position and to whatever you're about to add. Remove the leaving group from what you're adding, and then just add the carbon chain. And boom, no mechanism, no time wasted, but you got the correct product. What do you think of this method for solving a problem like this? Question. So basically B2H6 gives you an aldehyde if it's a terminal carbon. Yes, it's funny your name is Big Al, because I actually have a friend who goes by Big Al, and he's coming over, well, not tomorrow, on Saturday. Okay, so where was I? Here. It's not just B2H6. It could be anything with boron. So options are BH3. B2H6 is just 2 BH3s together, 9 BBN, and there's one more that most of you don't have to know. So these are the ones to recognize. Don't get freaked out on the exam if it doesn't look familiar. Just ask yourself, is there a boron reacting with an alkyne? I know what to do. Treat it like a hydroboration reaction, even though I don't recognize exactly what that is. Question. I thought it was impossible for secondary or tertiary halides to be used because they undergo elimination rather than substitution. No, Abdul Malik, that is incorrect. A secondary and tertiary can undergo substitution and elimination. tertiary will not undergo SN2. Secondary will. I'll be happy to go into that in more detail in the upcoming substitution elimination live, but I just want to make sure that's clear. All right, I think we have time for more. What do you think? More problems? Let's see. Can I get a bunch of hearts in the comments, and then we'll do some more. We'll do another problem. Ooh, should we do not too tricky. Let's go not too complicated. What if I give you a starting molecule that looks like this, and I ask you somehow, some way, to give me a final product that looks like this? However many steps you need, whatever reagents you need, go for it. Abdul Malik, there is no such thing as a dumb question. I had a professor who used to talk down to us and make us feel stupid for asking, so guess what? We stopped asking and we stopped learning because we were always afraid of getting talked down to. No question is a stupid question. You asked something, you learned. Turns out you already knew that. Great, but what if your next question is something you don't know and you ask and now you learn something? So I will encourage you to never apologize for asking a question. Going back to the problem, I have to consider, do I know of a reaction that will turn an alkyne into an alcohol? Well, first, did anything else change? How many carbons do I have? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 and 5 means I didn't do any kind of chain elongation, so I can't think convoluted. I have to think of just an easy transition. The problem is, I don't know of a reaction that will give me an alcohol from an alkyne. And so instead, I'm going to do what I did before and say, what if I don't think about my product, my reactant, and I just think about my product? What reaction do I know that can give me an alcohol from anything that maybe sorta kinda could be related to an alkyne? Well, I know how to do an alkene reaction that will give me an alcohol. So let's see what that alkene would have to look like. All I need is a pi bond here. If I have a pi bond here, then I do a very simple hydroboration, kind of like what we saw before. Step 1, BH3. Step 2, NaOH, H2O2, could add H2O. That will give me an anti-Markovnikov alcohol addition. And then I revisit the problem as if it's a new problem. What reaction do I know that will give me an alkene from an alkyne? Alkene from alkyne is a partial reduction. Because it's terminal, it doesn't matter which partial reduction I do. So H2 Lindlars, because why not? And that's it. H2 Lindlars will give me an alkene at the end. Then I react it with BH3 and NaOH, H2OH2, H2O2 for hydroboration. Let me just put the title here. And that's my final product. Alright guys, I think we have time for one more. Why don't we end with a couple of simple problems, kind of like a cool down, to make sure that we're not leaving overwhelmed. Okay. So I consider this an easy problem, but the reason I put it on the worksheet is because professors love to throw in rings just to scare you. If I react this right here with lithium in liquid ammonia, what do I get? Lithium in liquid ammonia, once again, is dissolving metal reduction. Your professors are more likely to show it with sodium, but it can also happen with lithium, and I've seen students lose points because they had no idea what to do. Lithium, just like sodium, is a group 1 metal, a radical when it's neutral, and therefore gives me a very reactive partial reduction to a transalkene. I redraw my chain exactly as I see it. I have 4 carbons, 1, 2, 3, 4. Trans at the pi bond here between carbons 2 and 3. 1, 2, 3, 4. Excellent. And that's my final product. All right, let's do another one. What if I ask for the starting alkyne for a product that looks, well, this time I'll give you the reagent, and that is HgSO4 with H2SO4, and my product looks like this. Description, you could have used Na or lithium. Yeah, the metals are interchangeable on paper. I don't know if one is more expensive in a real lab, but on paper they're interchangeable. You are very welcome. Emma says, my professor almost exclusively shows reactions with rings. When I see a chain, I get nervous. Emma, going back to that last problem, here is my challenge to you. When you see the ring, I want you to ask yourself, can I solve this if I cover the ring? And then you just add the ring back. More than half the time, it's going to make the problem so easy that the ring is just there. And another question on the last one. No, this is not the same as H2 with metal. So for example, if I reacted this with H2 and PT, that will give me a complete reduction because there's nothing to slow it down. Every single pi bond gets broken, and what I get here is hydrogen, 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 hydrogen for just a straight chain on the ring. So going back to this one, HgSO4 and H2SO4. Oh, I guess we shouldn't say starting from an alkyne, we just have a question mark. You should recognize that the ketone came from the acid catalyzed hydration using mercury, so oxymercuration, followed by ketoenol tautomerization. I have the option of getting two different alkynes in this problem. I could have done an alkyne that looks like this, or an alkyne that looks like this. So if the question asks, give me two potential starting products, all you do is ask yourself, what did the ketone come from? It came from an alkyne. Could I have gone in this direction? Yes. Could I have gone in this direction? Yes. Sometimes the answer is no, because in the case of the previous problem that we did with hydroboration, one side would have required oxymercuration because it would have gone more substituted. The curved arrow mechanism, if your professor requires it, definitely learn it. Can you use the annotation metal instead of PT? Yes, a lot of professors will do that, so instead of PT, they will just show metal, like that. Alright, as a reminder, to get the worksheet for tonight's practice set, along with the PDF notes, as well as to get notifications for upcoming live sessions, go to the pinned comment and click on the URL layerforsci.com/orgolive. That's where I'll embed the link to the video for every upcoming live stream, and that is also how I will know whom to send the notes to. So you'll get the notes and the worksheet probably within the next half hour. Okay, so with that, we'll go ahead and wrap up. As a reminder, I have a program called the Organic Chemistry Study Hall, and that is where I work with students a lot more one-on-one. We do live sessions like this, but it's a small group, usually 3 to 5, maybe 10 students will show up at a time. I get to see all your questions. I get to do a lot of practice problems based on what you ask. You get access to the entire video library for all the past sessions, and you also get access to my private tutoring and support group where you can post your daily questions. You don't have to wait for a live. Just post your questions, and that is where you'll get tutoring help every day on anything organic chemistry that you're stuck on. The link is layerforsci.com/join, and if you have any questions on anything we discussed today, leave it in the comments or email me. and I will see you guys next week. Have a wonderful evening and take care.